To continue, we have to Professor Felipe Chavez introducing to Professor Laurel Ohm. You can start, Felipe.
Okay, thank you, Juan. So thank Laurel for accepting our invitation to participate in our seminar. It's a pleasure and an honor for us to have her here. Laurel is now a professor. I as understood, a recent started as a professor in the University of Wisconsin-Madison in the US. Before that, she was at Princeton as a postdoc and at the Courant Institute in New York. And she did her PhD in 2020 and at the University of Minnesota. And Laurel is a specialist and interested in analysis of PDEs, more precisely in biofluid mechanics. So it's a very, very interesting topic. And I hope everybody enjoy the talk we are going to have here. So thank you, Laurel, and you can start.
All right. Thank you. Thank you so much for the introduction and for the invitation. And so, yes, so I'll be talking about some PDE problems arising in thin filament hydrodynamics. So just to kind of set the scene for the types of, or the fluid regime that we're interested in. So here's a video of a sperm cell that's swimming along in a very, very viscous fluid. And it's propelled along by this very slender flagellum that's interacting with the surrounding fluid. And so what I'll be interested in this talk is really models that seek to describe this interaction of the very thin structure like a cilia or flagellum with the surrounding very viscous fluid. So where I sort of sit in this, I mean, you can really talk about modeling this type of fluid structure interaction from many perspectives, from sort of very applied to really the PDE side of things. And what I'm really interested in is really developing the PDE theory of filament hydrodynamics. And so some of my goals are to more precisely determine the regimes of validity of some popular models that are used in thin filament hydrodynamics, and then hopefully this can inform derivation of novel models. And the approach that I'll take in this talk is to take some basic mathematical models that are used primarily for numerical simulations and try to justify them from a mathematical standpoint. And here I'll be focusing on two aspects of this question. First of all, in the static setting, so just a static filament. How can you describe sort of the forces acting on this filament from the surrounding fluid, and then also getting a bit into dynamics and how we can talk about this fluid structure interaction in a dynamic setting. So just to start off with, I want to start in the static setting where I summarize my work under the title Mathematical Foundations of Slender Body Theory. So what I'm going to start with is building up, first of all, what is slender body theory? And second of all, how can we understand it really from a mathematical perspective? So where slender body theory comes from, so let's consider the following setup. So we have a very thin filament here. So an example given here. And for now, I'll just be considering a closed filament, so no endpoints to this filament, although you can consider free ends as well. It just adds an extra layer of complication. But for now, for simplicity, we'll consider a closed filament with a constant radius epsilon. All right, and we have this filament, it's immersed in a very, very viscous fluid, which is well approximated by the Stokes equations. So outside of the filament, we have the fluid pressure, P, and velocity, U, satisfy Stokes equations. And then, okay, so that's what's going on outside of the filament. And then if we wanted to most accurately capture the interaction of this thin filament with the surrounding fluid, we would then want to prescribe some boundary conditions over the surface of this filament to describe how it's interacting with the fluid. However, because we're interested in very general shapes that are changing over time, this quickly becomes very computationally intensive to actually implement boundary conditions over the entire surface of the filament. And so this is where slender body theory comes in. And so it's really developed as kind of a computational tool to approximate the interaction of this thin structure with the surrounding fluid. And so the idea behind this approximation is to, all right, it's a thin curve. Let's just approximate it as the interaction of an infinitely thin curve with the surrounding fluid. So this is kind of the first level of the approximation, is to say, okay, what's the interaction of an infinitely thin curve with the surrounding fluid? And so to describe this interaction, so if we have some point forces just distributed along the center line of the filament, then we can just convolve those with the Green's function for the Stokes equations in free space. And so that's given by the Stokes lit here, this expression. So we can just take these point forces, integrate them along the center line of the filament, and that gives us kind of a first approximation to what the corresponding fluid velocity would be around that filament. All right. Okay, but this is sort of the coarsest possible approximation. It's not there's nothing yet in this approximation to really tell the fluid that there's actually a three-dimensional structure immersed in it. And so what's commonly done for computations is to add an additional correction to account for the fact that there's actually a three-dimensional structure there. And so what this correction serves to do, or the idea behind this correction, is that you want to enforce that as closely as possible, the fluid velocity over each cross-section of the filament is as close to a constant as possible. And so to see why you might want to prescribe something like this or enforce something like this, you can imagine that if you looked at the surface of the filament, so on the actual surface of the actual three-dimensional filament, or where it's supposed to be in this approximation, if you actually look at this surface and the velocity field of the fluid is not constant, so it looks like this, for example, then in the next time instant, your cross-section would deform. In this case, it would grow, right? And of course, okay, we don't want that. We don't want that to be happening over time. We don't want our cross sections to change their shape over time. And so what's commonly done to enforce this is to add a higher order correction that to leading order enforces that at the filament surface, where the actual filament surface should be, there's a correction that's enforcing that the fluid velocity is as close as possible to just a constant. Right. Okay, so together, integrating this force density along with these Stokes-lit and doublet factors gives an approximation to the fluid velocity outside of the filament. And then if you want to use this expression to obtain an expression for the velocity of the filament itself, you can do a matched asymptotic expansion about epsilon equals 0 to obtain an expression that's valid on the center line of the filament. So you can't directly evaluate this expression on the center line, but if you expand about epsilon equals 0, you can obtain an expression that you can actually directly evaluate along the center line of the filament. So this gives us sort of a nice way of approximating the velocity of the filament itself due to prescribing some point forces along the filament. And so we get this expression in terms of a local matrix multiplication plus this non-local operator along the length of the filament. All right. And so it's this centerline approximation that commonly gets used in numerical simulations to approximate the motion of a thin filament in a three-dimensional fluid. All right. But where my questions start is really, so this is all an approximation, right? We're sort of really starting with this assumption that we are approximating the interaction of the fluid with the filament as the interaction of the fluid with really a one-dimensional curve. So we're just prescribing this sort of these point forces only along a curve. And so I want to ask the question, how close is this slender body approximation to some notion of a true solution? So as I mentioned, right, we're given this data, this force data, that's prescribed only along a one-dimensional curve, right? And so given this force data along a curve, we somehow want to be able to solve for the surrounding fluid velocity as well as the velocity of the filament itself. So the sort of immediate difficulty here, or what appears to be sort of an issue here, is that it's not really clear how we can actually formulate this problem as a well-posed PDE, because we're just given data that's along a curve, and we somehow want to be able to solve for a three-dimensional boundary value problem. Right? So it seems like we don't have enough information. Right. So the question becomes then, what exactly are we approximating with this slender body expression? Right. So to answer this question, we developed a notion of a slender body PDE, or slender body boundary value problem. So now I want you to consider really a truly three-dimensional filament, right? So it does have some actual thickness epsilon, right? And so this filament with an actual thickness, it's immersed in a Stokes fluid. So outside of the filament, we still have just the homogeneous Stokes equations. But then on the surface of the filament, now we have this 2D surface, I want to prescribe some sort of funny looking boundary conditions. So the first condition that I'm going to prescribe is that if I sum up the force, so really the Neumann boundary value of the Stokes flow, if I take the Neumann boundary value, so sigma n, so that's the surface stress, if I take that and sum that up, integrate that over each cross section, that should give me my force data F. Right, so I'm interpreting my force data prescribed along a curve as the total surface force per cross section. All right. But then, okay, as we mentioned, just having that piece of boundary data alone is not going to be enough to actually have a uniquely determined boundary value problem. So what I need to do in addition to this is also strictly enforce this fiber integrity condition, this condition that cross sections should not be deforming over time. So to enforce this strictly, I enforce that the velocity at the boundary of the filament is only a function of arc length. So it's independent of the angle over each cross section. All right, so in particular, you have velocity field that is constant over each cross section. Right. So in particular, I end up with a boundary value problem where I have no pointwise boundary information, but I have these two average sort of boundary conditions. So I have this sort of partial Neumann boundary condition and this partial Dirichlet boundary condition where, okay, I don't know what this velocity is, right? That's something to be determined. But what I do know is that it's constrained to be independent of the angle over the cross section. All right. And so why does this appear to be a good formulation why does this appear to be the right way to think about slender body theory as a boundary value problem? So first of all, this boundary value problem satisfies a very natural energy identity. So on the left-hand side, so if you take your Stokes equations, multiply by U, integrate by parts, right? So on the left-hand side, you get the viscous dissipation. So throughout the fluid domain, the energy that's dissipated due to the viscosity of the fluid on the left-hand side. And then on the right-hand side, where we do have our boundary terms, because of how we've defined our boundary conditions, instead of having an integral over the surface of the filament, because of how the boundary conditions have been defined, this reduces to an integral just along the center line of the filament. So of the velocity times the force along the filament. So this is the power that's exerted by the slender filament on the fluid, right? So we get that the viscous dissipation balances the power exerted by the slender filament. All right. And so from this energy identity, we pretty much automatically get existence uniqueness of solutions from Lax-Milgram, as well as a corresponding energy estimate. All right, so just given that force data prescribed along a curve, we can actually control the resulting Stokes flow around the filament. All right. But there's a little bit more to unpack here. In particular, we'd like to be able to use this energy framework to be able to talk about the error between this boundary value problem, the solution to this boundary value problem, and this approximation that is used in the computational literature, this slender body theory. So in order to do that, we have to be a little bit careful because there's this constant appearing in the energy estimate, and we have to dig a little bit more deeply to see exactly how this constant actually depends on the filament radius epsilon as epsilon goes to 0. And so there's a few places where we have to be a bit careful. The one I'll mention in particular is that actually the trace inequality, we have this sort of quasi one-dimensional trace inequality that actually blows up like root log epsilon as epsilon goes to 0. So this is something that needs to be accounted for in the energy framework in order to, at the end of the day, obtain an error estimate for slender body theory. So just to summarize the well-posedness theory of this slender body boundary value problem, we have existence and uniqueness of solutions, and we have an energy estimate where solutions are bounded by our prescribed force density with a factor that depends on root log epsilon as epsilon goes to 0. Okay, so with that, we can move on to really the big question, which is how does slender body theory actually compare to this notion of true solution that we've developed? And so to answer this question, we can use the slender body theory expression, which I've written out in a bit more detail here, just to kind of show how many terms are actually showing up in this expression. To compute, so we use this expression to compute two sources of errors. So there's two sort of residuals that are appearing with respect to this boundary value problem. So the first source of error is that if you take this expression and actually evaluate it at the surface of the filament, so where the surface of the filament should be, there is some angular dependence. So it's not completely constant over each cross section, but we can bound the error there. So the amount of angular dependence at the filament surface, we can bound that by epsilon log epsilon. And then there's some error in computing then the total force density that this expression gives rise to. But that can also be bounded by an expression proportional to epsilon. All right. And putting those error sources together, then we can obtain a full error estimate for the slender body approximation with respect to this notion of slender body boundary value problem that we've developed. So the difference between the slender body approximation and the solution to our boundary value problem satisfies this error estimate as epsilon goes to 0. So in particular, as epsilon goes to 0, the slender body approximation approaches the solution to this boundary value problem as epsilon log epsilon. All right, so we get this sort of estimate of the difference between them for small values of epsilon. All right, and so this first estimate is valid in the bulk fluid away from the filament, and then we can also consider, okay, what about the expression for the velocity of the filament itself? If you take that expression and compare it to the trace of the solution to the boundary value problem, then we also get that the difference between those goes to 0 as epsilon goes to 0, with an additional factor of root log epsilon appearing from the trace inequality. All right. So in particular, we have a means of justifying this slender body approximation that appears in computations from the perspective of an actual well-posed boundary value problem. I'll just mention briefly some applications and extensions of this framework. So that was all stated for closed loops, but you can do essentially the same analysis if the filament has free ends, as long as your radius decays smoothly at the endpoints, decays to 0, and your force density has the same rate of convergence to 0 at the endpoints. Then some extensions to considering rigid fibers and a related method of regularized Stokeslets, as well as a layer potential formulation of the slender body PDE, which we used to develop a sort of a detailed numerical method based on this. All right, so from here, I want to switch gears a little bit and talk about what I call the slender body inverse problem. So far, we've been considering this, what I call the forward map along the filament center line, which is where you prescribe some force density along the filament and use the slender body boundary value problem, or use slender body theory to solve for the velocity of the filament. And so for this problem setup, you prescribe the force, solve for the velocity. We showed that the slender body approximation is a good approximation of this notion of boundary value problem solution that we've come up with. But it's sort of, it's an equally valid question to ask about the other direction. So what if we want to prescribe the velocity of the filament and solve for the forces along the filament? All right, so in particular, what if we would like to somehow approximate the inverse map? So mapping from a theta independent velocity along the filament to force density along the filament. Right. And so from a PDE perspective, this is actually a much simpler question because it's just the Dirichlet problem for the Stokes equations. We just happen to be only prescribing Dirichlet data that's independent of the angle over each cross section. So our Dirichlet data, we're only choosing Dirichlet data within a particular class, but it is just the Dirichlet problem for the Stokes equations. So from a PDE perspective, it's actually much simpler because, well, of course, we have very well-developed theory for the Dirichlet problem. But the difficulty here is actually in the slender body approximation itself. And so if we go back to this integral operator along the filament center line that's used in numerical simulations. So if we look at this operator itself, it turns out that trying to invert this operator to solve for f given u is actually an ill-posed problem. And so, but because the forward problem worked so well, we want to dig a little bit deeper into the nature of this ill-posedness to kind of figure out, okay, what can we still salvage from slender body theory to approximate this inverse problem. And so to consider this question, I'm going to be thinking about a model scenario, so an important model geometry, which is just the straight but periodic filament. So I'm considering, so of course, a non-physical scenario, but it's a very instructive one where I can actually say a lot about the solutions to both the boundary value problem and the slender body theory. So in this very simple geometric setting, I want to consider the eigenvalues of this map. So it's kind of an angle averaged Dirichlet to Neumann map along the filament center line. So the idea is, okay, I'm looking for the eigenvalues here that satisfy my total force density equals lambda times my velocity along the filament. Right, so I'm looking for the eigenvalues of this map, and it turns out that in this particular geometry, things are actually explicitly computable. So the eigenfunctions are just exponentials, complex exponentials, and they decouple into the tangential direction along the filament, so the EZ direction, and then the directions normal to the filament. And I can explicitly calculate what these eigenvalues look like in terms of sort of nasty looking ratios of modified Bessel functions. And okay, these expressions look nasty, but they're explicit. And actually, because Bessel functions satisfy a lot of nice properties, we're able to show nice linear growth bounds on these. So in particular, what this operator looks like is really like the usual Dirichlet to Neumann map, right? So it's akin to taking one derivative along the filament. All right. Okay, and so, but let's compare this this inverse operator to what happens when you try to use slender body theory in this setting. So again, for the straight periodic filament, we can calculate the eigenvalues of this operator. And it turns out that in both the tangential and normal directions, we have this blow up in the eigenvalues at finite wave numbers. So there's a place where the denominator crosses 0. All right. So in particular, at high wave numbers, we're having, well, slender body theory behaves horribly, right? So this is at wave numbers that are proportional to, so it's very high wave numbers, proportional to 1 over epsilon, right, is where this blow up occurs, all right? However, we can note that down at the low wave numbers, slender body theory is an almost perfect approximation of the eigenvalues of the PDE operator, right? So the eigenvalues of the PDE operator are growing linearly, and they agree very, very well with slender body theory at low wave numbers. Right? And so we want to exploit this low wave number agreement. So we can consider 2 types of regularization for the slender body operator. The first is a truncated Fourier series, right? So we can consider just truncating the Fourier series for this operator at some finite wave number before we run into this blow up issue. And so this is this exact type of regularization we can only explicitly do in this model geometry because we have a Fourier series representation of it. But what this regularization mimics, or really does, is it really mimics the effect of numerical discretization, where you're cutting off beyond some finite wave number. All right, so we can truncate the Fourier series, and we can also consider adding a regularization into this integral operator that's appearing in slender body theory. So I call this the delta regularization. It just involves inserting a small regularizing parameter that's proportional to epsilon in the denominator of this singular integral operator that was appearing. And so let me just mention what we can calculate the spectrum of this operator as well in our model geometry. And again, we get good agreement with the slender body PDE at low wave numbers. And then, okay, at high wave numbers, we're just asymptotically approaching some bound rather than growing linearly. But in particular, these eigenvalues are only diverging linearly from the PDE eigenvalues as the wave number goes to infinity. So just to summarize what we can do with both of these regularizations is that, okay, both of them then yield good approximations of the inverse problem for the slender body PDE, right? So the difference between the truncated operator, using the truncated operator versus solving the boundary value problem is proportional to epsilon squared, given sufficient regularity on the Dirichlet data. And then the delta regularized operator as well also converges to the PDE solution as epsilon goes to 0. Right. Okay. So from there, I would like to segue into talking about dynamics, because really the first slide that I showed was really okay, there was a lot of dynamics going on in that setting. And so we really developed the theory pretty precisely in the static setting. We'd like to be able to use that to understand the dynamics of things like this sperm tail interacting with the surrounding fluid. And so you can formulate this as a free boundary problem, and I'd like to talk about that. So we've succeeded in making sense of this map from taking force data along a curve to well, a velocity field along the filament in 3 dimensions. All right, and so we can put this together to create a dynamical free boundary problem. All right, so if we take this map and couple it with a no-slip boundary condition, so that, okay, the fluid velocity is actually just the velocity of the filament, and impose a nice, simple, elastic forcing along the filament. So take Euler-Bernoulli beam theory, for example. So this is kind of really saying, okay, the filament wants to minimize its curvature, coupled with an inextensibility constraint. So it doesn't want to grow and shrink in length over time. Then we can consider this evolution problem where we are evolving the filament position in time according to, okay, so the forcing is given by the Euler-Bernoulli beam theory, and the map that's taking the force to the velocity is given by the solution to our slender body boundary value problem. Right. And of course, you can consider, as people do in computations, you can consider approximating this map using local or non-local slender body theory. And so let me just kind of show what the dynamics are if you are just using local slender body theory, which is just ignoring the integral part of slender body theory. So you get these kind of dynamics. This is, of course, with some periodic forcing, but you get these filaments, and these are free-ended filaments as well. You can say a lot about this evolution when you're just using local slender body theory. So there, it's just a matrix multiplication, and you can say pretty much everything you want to about well-posedness of the dynamic setting here, and you can even say some things about when you get the filament to actually swim, as in the right-hand side, versus where it just flaps around in space over time. So we can say a lot of nice things in that setting, but it would be really nice to actually be able to say something about a full free boundary problem where we're using actually that notion of sort of angle averaged Neumond-Dirichlet map that we've developed using the slender body PDE. Oops. So what can we say when we want to use this full map L epsilon, so the full slender body PDE solution, to execute this forced velocity map? So what can we say? Well, one thing is that we would like to be able to say that we still have this same really parabolic structure in this evolution equation that we do for local slender body theory. And so in order to say that, we need to be able to extract some detailed mapping properties from this operator L epsilon. And the nice thing about this setting is that we actually do have really, really, really detailed information in a particular geometry, which is the straight but periodic filament, right? So this is kind of similar in spirit to what's done in, say, the Muscat problem or for water waves, for example, where in those cases, when you want to think about a curved interface between say two different fluids, you take info from a straight interface and treat the curved interface as kind of a perturbation of a straight interface. And here in this setting, we don't have a completely straight interface, but we do have a straight cylinder that we can compare to. So we want to extract mapping information from this straight but periodic setting. And so I want to consider this in first the toy problem, where we just consider the Laplace equation. So we can consider the same type of slender body boundary value problem, but just for the Laplace equation. So outside of the filament, you just have Laplace u equals 0, and then on the surface of the filament, the total Neumann data per cross section is equal to some scalar f, and the value of the Dirichlet data is constrained to be independent of the angle over the cross section. Right, so the same setup, but just for the Laplace equation. And so now we can consider this map about the straight but periodic filament again. And again, we can calculate exactly what the eigenvalues for this map look like. So we just get one Fourier multiplier that's corresponding to this map in the straight periodic setting, as ratio of modified Bessel functions again, a much simpler ratio. And what we can do with this is, okay, first of all, extract some mapping properties in Holder spaces for that. But then also what we can show is that actually this explicit information that we have is actually really the leading order gives you the leading order mapping properties for a curved filament as well. So really fully understanding the straight periodic setting really gives you pretty much all the information you need for a curved filament as well. So what we can show is that this angle averaged Neumann to Dirichlet operator that we have is actually can be decomposed as the straight filament plus a remainder that's small in epsilon. So this piece is small in epsilon, and then plus a remainder that's smoother. Right. So really the leading order behavior is given by this straight periodic operator. All right. And I'll just mention briefly what goes into the proof of that. So that comes out of writing this relation between F and U in terms of layer potentials along the surface of the filament. So relating U and F through the single and double layer potentials along the filament. And the nice thing in the straight periodic setting again is that we can actually explicitly calculate the symbols for the single layer and the double layer potential, which is extremely nice and unexpected. Oops, sorry. And then we can consider decomposing this slender body, the slender body Dirichlet to Neumann map as the straight periodic setting plus some remainder terms that we can bound. Right. Okay, and so just to kind of summarize where this is all heading, the idea is that hopefully we can be able to tackle, this will give us a blueprint for tackling the filament evolution problem by being able to decompose the full operator for the Stokes setting in the same way. So as long as we can extract the straight periodic, we expect that we can extract the straight periodic filament as the leading order behavior of this map, plus lower order remainders. And from that, we should be able to, then extract the leading order behavior. So it should be giving us then a third order parabolic equation for the evolution. And so that should allow us to establish local and time well-posedness for the filament. And it would be nice to consider both extensible and inextensible filaments, as well as the limiting dynamics as epsilon goes to 0. All right, so it'll be easiest to first consider an extensible filament, but then adding inextensibility is kind of the next step. And then really being able to, hopefully at the end of the day, establish really a full hierarchy of models, starting from 3D elasticity and getting a limit to hopefully this slender body PDE, maybe in some asymptotic regime, and then all the way down to local slender body theory. And so that's the end of that. And thank you for attending, and thanks for any questions.
Okay, thank you, Laurel. It's a very, very interesting talk. So we will open now the mic for anybody who wants to make any question. If you guys want, you can also use the chat, so I can read, or even Laurel directly. So, pessoal, se alguém tiver alguma pergunta, algum comentário, alguma pergunta, algum comentário, si quieres pueden usar el chat o usar directamente el micrófono. Okay, Laura, I just have one question, but maybe it's a bit naive, but would it be possible to try to control the shape of the filament, like try to make it better, so it to give you more to do something like make it where could you put a control to control the shape of the filament, for instance? What would be a natural control?
Yeah, definitely. So it's definitely possible to do that. I would say so. Oops, so understanding it from a PDE perspective is maybe, or in this framework is maybe not the easiest way to do that. But if you did want to do that, if you go back, let me just show this one again. So in here, in these, and so actually we're you can do this using local slender body theory. So the simplest sort of approximate setup for this. And you can, so in this case, we're forcing this with a preferred curvature. So we're saying, okay, there's some time-dependent, time-periodic preferred curvature that this filament has, and it's trying to reach that over time. And so that's what's giving rise to the dynamics here. And so you can put a control in the form of some notion of a preferred curvature that the filament wants to attain. And that's a way of really getting the filament to maybe perform a certain task that you would want it to do, or make a certain shape that you would want it to do. So you can put a control, it would appear inside this forcing term.
Okay, thank you. Pessoal, alguma outra pergunta, pessoal? Comentário? Any question, comments? Perguntas? Comentários? Okay, so I have no more questions, I think, because today here in Brazil it's holiday, so maybe people is at rest.
Oh, yeah, of course.
Okay, but thank you very much, Laurel. It was very, very interesting. It's very nice to see what you have been doing in your young career, but it's very nice topics. So hope to see you again soon in our seminar or in other events.
Yeah,
so thank you so much.
Thank you so much. Thank you all. Thanks. It's great.
Thank you, Felipe. Thank you a lot, Professor Laurel Ohm, for your brilliant talks.
Thank you.